slide right here. There are some genes that are just always on. Or in other words, this word constitutive, you're going to see it again a couple times, or well, throughout this section. It just means always on, not regulated, constitutively that way, just always in that direction. And it's just going to be like a housekeeping gene, which basically means things like glycolysis, variety of things that you just need always in your cell on at all times. Then you're going to need other ones that are regulated, and those are the cell-specific cell types, like especially when we get to eukaryotic. When we go to prokaryotic, it just means when maybe you have something available, that's when you turn on a gene, or how about like when you have enough of it, you can down-regulate it. That'll actually be the tryptophan story, is the idea is you make it, but then eventually you don't want too much of it. Supply and demand, classic business model, which stock market looks kind of bad. But the bottom line is, the idea is that supply and demand does fit this kind of game over here. If you don't have the supply, don't make something, right? You know, basically. So we're going to follow that theme, and then we're going to follow a very similar theme of what we've talked about before about where can you regulate. You can regulate at the transcriptional level, which means don't transcribe it if you don't want it, right? Or just cut it off. Then actually what you're missing in here, didn't mean to put it in there, is post-transcriptional. They have a little bit less. So this fits after you make the mRNA, you can still regulate it before you start translating. And that's kind of a subtlety that we'll follow in bacteria, but it's very, very clear in eukaryotes because of the nucleus separating things and processing steps. But we're going to cover that here. That's an intermediate. And then translation, you can like basically say, do I want to translate or not? And that's ribosome regulation, where the ribosome has access to it. So then that comes back here. And then post-translational means you've already made the polypeptide. Notice the word post. After translated, right? So follow the wording, and it'll help you kind of guide you. And that means at the polypeptide level, you can decide whether to activate it or inactivate it. You could even destroy it if you wanted to, and then you have to make it again. But a very classic way is keep the protein there, but just kind of activate it and inactivate it, kind of like a light switch, as I'm going to call it. You don't want to rebuild an electrical circuit. You would have like the light socket still sitting there with the light switch, and you go, I want it on now. Now I want it off. On, off, on, off. That would be your polypeptide being there, and you switch it between those two states. Okay, so those are where we're going. And then after that, we'll switch to eukaryotic, and we're going to find out the complexity is they got a lot of these same things going on, and then we're going to stack a couple more things on there of like some complexities that are involved. All right, so we're going to spend a bunch of time here, the transcription level, because it is very efficient to regulate at this place. So meaning like 2,000 genes, don't turn them all on, first of all, right? So that's about E. coli's level of how many genes they have. Only turn on a subset, you just need at all times. And then these, you decide when to turn on. And this would be best if you stop it before you even like start making the transcript, right? All right, so we end up in this category of repressors and activators. Now here would be one phenomenon. You can make an activator when you need it. It does its thing, activates things, and turns on genes. Then the activator gets degraded, and then it's no longer there. That's okay. That's a decent model, but it means that every single time you have to make the protein again. So this one actually is kind of like the on-off model, but for a transcription factor. Basically, these don't say it. Transcriptional regulation are done by transcription factors, which are proteins, right? And these are regulating not at the promoter itself per se, but at the actual regulatory elements. I'll write that up. Now, I think I've said this before, but when you say the word element, what does that usually mean?
Protein.
No, not protein. the DNA sequence. If I say the word factor, then you say protein. So factors are proteins. The elements are the DNA sequences in which they bind, right? That's a pretty core concept right there. So RNA polymerase, what does it bind to? To initiate turning on a gene.
RNA primer.
Nope. RNA polymerase is going to transcribe where? It's looking for a
Start codon.
A what?
Start codon.
Promoter.
Oh.
Okay, so if anything's hazy right now, time to review exam 1 material. Because everything's back in play. Everything from exam 1. So cumulative means we build upon the past, and so it is still in play. So you have to understand, because actually later, attenuation, something was on a previous slide, you have to really know the difference between transcription and translation. If you don't, you muddy the two, you won't understand the concept. So don't let it go. Make sure you understand what we went through exam 1, okay? All right, the idea of negative control is just a concept that means to kind of slow things down, right? Kind of inhibit. There's a couple different ways you can do that. In essence, activators are typically going to be used to push it, to make it, right? So that's all this really means, but we kind of use those terms sometimes, and it'll come back to that. Okay, now here's where it gets interesting. Now we're actually going to do kind of like activating and inactivating the particular protein. Not in the sense of activators and repressors per se, but whether the activator itself is going to do its job. Let's actually go back here. The activator's job is to bind to DNA and increase the transcription. If I turn off the activator and it's just going to sit around, it's not actively looking for the element, and it's not going to be doing that job. It's just going to sit around. It's what I call a sensor. In fact, both of these can serve as sensors. Let's think about a smoke detector. In fact, recently I had to put a bunch up in my house for passing inspection. The bottom line is, how many times do we just knock the battery out of that because it's just, ticking us off because it was beeping at the middle of the night, right? Happens to almost everyone in this room. But the question is, where do you put the battery back in there the next day? Because if you don't, it's not sensing. It's done. It's not a sensor. So basically, it has to be in a ready sort of state to go into like sensing whether smoke is there. So right now, it's present and it's sensing what it's being told to do. So it's going to wait around. Okay, I'm supposed to activate. It's going to be told to do that, activate. And then it's going to be told to, hang out for a bit. All right, I'll do that. Same thing over here. The repressor, it's going to be sitting there sensing. It's up there on the ceiling, right, sensing smoke. And then it's going to say, hey, I need you to repress, okay? Does that. It says, I need you to release. Okay, I'll do that. So it's not just doing one job of just repressing only. It knows also how to release. It's going to be in an on or off or active state, I would call it, in whatever it's trying to do. And how is it going to do that? By the word up here. I would circle that word right here, effectors. Effectors are what we call an allosteric binding site. We've actually used that word before, right? The allosteric model for how RNA polymerase fell off and terminated, right? So that was one of the models. You had torpedo and allosteric. Okay, so if I draw a protein, and this little notch is where the effector goes. It's going to affect, now this right here will be like the business end of what it's supposed to do. Is it an activator or is it a repressor? In this case, we'll follow this theme right here. So if it's an activator, this would be a binding site for DNA. Or in other words, what I wrote up on the board, the DNA, the regulatory element. Okay, so it either sits on that sequence, matches it up, imagine the sequence of DNA right there, either lands on it or it does not. It has a choice. Now, sometimes the activator is active just from the get-go. You make the polypeptide and it's hungry, or it basically wants to go bind to the DNA element. You don't have to do anything to affect that. The opposite would, then you would say the effector, when something binds in that pocket, and it's not, this is reversible, meaning like it's not a covalent interaction. And it's usually a small molecule interacting with it. And this small molecule will then tell it to either release, it would actually change its conformation so it can no longer bind, or it actually does the opposite. It didn't bind first, it didn't bind at first, and now when the effector comes in, it snaps in and actually looks for the place. So it's either or, and you're actually going to see an example. I'm going to run through all 4 options for basically the activator repressor situations. Okay, so when we talk about it actively making something, so that the effector, when it actually hits the repressor or the activator, we call it induce. So it means that whatever's going on, both of them are just kicking back. And you're like, wait for it, an effector hits, and they either bind to the DNA to activate it, or in the case of the repressor, they release, because they're going to be permissive to allow the DNA to transcribe. So that means you're making it. Induce means to make, right? Inhibit, obviously, that's pretty straightforward. The repressor might be back here waiting, and then all of a sudden the effector hits it, and then it actively binds. Whereas the opposite happens for the activator. The activator's on it, and then when the inhibitor hits it, you pull off the gas pedal and you decelerate, which means you inhibit. So these are reverses of each other. The activator here needs to be told when to bind. This one is already bound and it gets pulled off, and vice versa for the repressor. All right, so here's the pictures that show that. Here's a repressor protein that binds right when it's made. There's your effector site right there. So right now, it's at the position that we're going to call the operator. There'll be a little place right there. It's not outlined on this slide, but you'll see it later. The operator is exactly what a regulatory element is. It has a binding site right here where they're interacting. So it's like searching for that sequence, locks in on it. We've talked about those over and over again, right? So when the inducer hits, whatever that equals, a signal, it's saying release. And now RNA polymerase can go. Okay? Now this is the inducer type for activators. Activator is not active right now, meaning it's just sitting back waiting. Then when you get the signal, it's saying, oh, you know what? It's time to go. So the inducer hits it, and now it binds. Let's do the reverse. The repressor's off from the get-go. Oh, what was out here? The repressor's on. No, the repressor is now officially off when it's just made as a polypeptide. Then it takes the signal, which we're going to call it a co-repressor because it has to be present to repress. Then it actually finds its binding site. This is the opposite too for the activator. The activator's made from the get-go. It goes and finds its binding site, and it's promoting or increasing the amount of transcript, activating it. It gets a signal, and there's the word that seems really appropriate, inhibits it. It inhibits it from binding to its site. So let's be very clear. It's as important to decelerate than it is to also put on brakes if you're talking about repression. If anybody's driven an electric car, I'm sure most people, a lot of people have had the chance, maybe you haven't. But if you take your foot off the accelerator, what typically happens? You don't usually coast like you do in other cars. You usually decelerate. In fact, this is the way I think about it. If you're driving a race car, just say you're driving a really fast car, and you're going to come around a turn. If you slam on your brakes, you're going to get squirrely. You're going to go off the track. What would you do if you're a really good race car driver? You decelerate by just putting your foot off the accelerator. You decelerate into the turn because you're, and then you're not hitting the brake, which makes you go squirrely, and you come around the turn. So pulling your foot off the accelerator